welcome to another lecture on the course on 3G and 4G wireless mobile communication systems. In the last lecture, we had started looking at multi-user CDMA, that is how different users can be multiplexed on the downlink of a CDMA communication system. In particular, we had said that they use different codes and the cross correlation between those two different codes is given as follows. The cross correlation between the code C0 and of C user 0 and C1 of user 1 is denoted by R01 and K denotes the lag of the cross correlation. We said these codes are independent of each other, hence the cross correlation, the expected value is 0 and the variance or the power in the cross correlation, this looks like noise of variance 1 over n. That is the first thing we said. We also said that if I look at the SNR of the downlink at user 0 in a 2 user CDMA system with user 0 at power P0, user 1 at power P1, then the SNR is P0 over P1 plus n. So, I have a multi-user interference component arising from user 1. However, that interference is suppressed by a factor of n. Similarly, there is a noise which is sigma w square over n. The noise is also suppressed by a factor of n. Hence, I have the net SNR which is P0 divided by P1 plus sigma w square into a factor of n, which is nothing but the length of the spreading sequence. This is also known as the processing gain of a CDMA system. Okay. The other thing we said in the last lecture is that we started with what are the advantages of CDMA compared to other communication systems or other communication multiple access schemes. We said that CDMA is very resilient or it is very robust to jammer or jamming suppression, or because if there is jammer who is trying to jam your communication system with power Pj, that is the huge power of the jammer, then in CDMA that power of the jammer is suppressed by a factor of n. Hence, the effect of the jammer or the adverse effect of the jammer is substantially reduced. That is why CDMA is very robust or resilient to interference by a jammer. Hence, we also said one of the first uses of CDMA was in secure communication. It was extensively used in military before coming into the civilian domain for this precise reason, that it is resilient to jamming, resilient to the adverse effect of jamming. We also started with the second advantage of CDMA, which we said is graceful degradation, and for that we started by considering a CDMA system which has capital K users, and we saw what happens when a k plus 1 or one user is added to the CDMA system, and we said that this added user causes an interference of P capital K plus 1 over n. That is, out of the total power of P capital K plus 1, only a fraction, that is 1 over n of this P k plus 1 is affecting the user 0. Hence, this user, the k plus 1th user, causes an interference of P k plus 1 over n at user 0. Now, let us continue this thought with today's lecture. So, now what about at the rest of the users? P k plus 1, the user k plus 1 is causing an interference of P k plus 1 over n at user 0. So, k plus 1th user is causing an interference of P k plus 1 over n at user 0. Now, remember user 0 is nothing special, because P k plus, because at user 1 also sees k plus 1 user as an interferer. So, user k plus 1 will cause an interference of P k plus 1 over n at user 1. Similarly, he will cause an interference of P k plus 1 over n at user 2, and so on and so forth. So, in fact, I can generalize this as saying user, in fact, I can generalize this by saying user k plus 1 will cause an interference of P k plus 1 over n at each of the users 0, 1 up to k. That is, this user of index k plus 1 will cause an interference of p k plus 1 over n at user 0, p k plus 1 over n at user 1, so on and so forth, p k plus 1 over n at user capital K. Hence, this interference caused by the user k plus 1 is not restricted to one user, but it is distributed amongst all the existing k users. So, let me write that point. The interference caused by the addition of a new user, namely the k plus 1th user in this case, by the addition of a new user is distributed, it is distributed amongst all the current users or amongst all the current users in the CDMA system, or amongst all other users, amongst all other users, all other in the CDMA system. Thus, the interference or the adverse effect of each new user is shared equally by all the existing users in the CDMA system. So the interference caused by the user is shared equally amongst all users. This leads to interference distribution. Hence, this leads to graceful degradation. Instead of the interferer affecting only one existing user, what is happening is this interference caused by the user is being shared by all the existing users in the system. So, it looks as if each user in the system is taking little bit of the burden of the addition of the user of the addition of a new user. Hence, the performance, hence the SNR of each user decreases slightly rather than the SNR of one user decreasing significantly and all other users being not affected. Hence, the addition of a new user causes the SNR of each user to decrease slightly because the interference is being shared across all the existing user. This leads to what is known as graceful degradation, because the addition of a new user is not affecting only one user and causing his SNR to drop significantly. Rather, this interference is being shared by all the users and each of them is accepting a portion of the burden, resulting in a slight decrease in the SINR of each user. This leads to graceful degradation. Alright, so this is the important property of CDMA. This leads to this interference distribution, in CDMA leads to graceful degradation, and this is a very important property of CDMA system. Now, how does graceful degradation is a very important property. Now, how does graceful degradation in CDMA lead to or what is significant about this graceful degradation, or why is graceful degradation important? Because that leads to another important advantage of a CDMA system, which is universal frequency reuse. So, let me talk about the third advantage. Third advantage in a CDMA system, which is the most important advantage of a CDMA system, which is universal frequency What does universal frequency reuse mean? First, let us talk about what universal frequency reuse means. Universal frequency reuse means, for instance, a cellular operator, whoever wants to operate a cellular network, is assigned a certain set of frequency bands of which he can allocate to the users. typically what is done in 1G and 2G systems are, if I have a group of cells, remember every cellular network consists of a group of cells. This you might have learnt from your basic course on mobile communications. I will divide my allocated frequency spectrum into different bands, allocate those different bands to different cells. For instance, I will allocate band 1 to cell 1, band 2 to cell 2, band 3 to cell 3. I will distribute the bands, because if I allocate the same band to neighboring cells, then the user who is transmitting in this band in cell 1 will cause interference in the neighboring cell, which is band 3. For instance, if same band, if same frequency f1, if f1 is allocated to both cell 1 and cell 3, user in cell 1 using that band and user in cell 3 using that band will interfere with each other. Then user in cell 1 on f1 will interfere with user in cell 3 on frequency f1. That is, what we are saying is, if the bands are not divided between the different cells, then the user in the adjacent users in adjacent cells on the same frequency will interfering with each other, thereby causing low SNR at the receiver. Hence, we will have a poor channel, hence there can be no decoding, hence the beta rate will be high, hence their call will be dropped, and so on and so forth. Now, as against this, so hence if I have a certain number of frequency bands, those frequency bands are divided amongst the cells. This is known as frequency reuse factor in a cellular network. You might also have seen this in your basic course on mobile communications. If I have a band, if I have a frequency band B that is allocated to the cellular operator, B is the band width allocated to the cellular operator. I can only use the fraction of that bandwidth in each cell in 1G and 2G systems. Typically, that fraction is 1/7. This is also known as frequency reuse factor. That is, only B/7, that is bandwidth, divided into 7 segments. One of the segment, that is B/7, is the bandwidth that can be employed in each. So, if a bandwidth of B is allocated, B/7 is the bandwidth that can be employed in each cell in a GSM system. Now, how is this different in CDMA? Now, let us come to CDMA. What is done in CDMA? In CDMA, let us again consider the same situation where I have 3 cells. That is, I have cell 1, cell 2, cell 3. Now, if frequency f1 is allocated to both these cells, if f1 is allocated to both cells, now remember in CDMA there is graceful degradation. Hence, if there is a user on f1 in this cell on the same frequency in this cell, his interference is shared equally by all users in the adjacent cell. So, user on f1 in cell 1 will cause an interference of P1 over n, that is the power transmitted, over n, which is the length of the spreading cord, at each user in adjacent cell. Hence, previously in GSM, where users will directly interfere because they are not transmitting on codes, in CDMA, even if you reuse the same frequency in the adjacent cell, the interference caused at each user will only rise slightly because of the graceful degradation property of the CDMA systems. That is, because we have the graceful degradation in which each user's interference will be shared equally by all the existing users. So, the SNR of each user decreases slightly rather than one user getting completely affected adversely by this neighboring user. Hence, what happens now, or what this results in, is that each frequency band or the allocated bandwidth can be completely reused in the adjacent cell. Hence, in CDMA, unlike in GSM, hence in CDMA all the bandwidth B can be reused in every cell, and this is a big advantage of CDMA. Look at GSM system. In GSM system, we said only 1/7 of the bandwidth can be used in every cell. In CDMA, the complete bandwidth B can be used in every cell, which means now I have 7 times the bandwidth in every cell. So, I can support 7 times more users in every cell, and that is the biggest advantage of CDMA, because I can reuse the frequency in every cell. Hence, I can support a much larger number of users compared to existing 2G systems. Hence, because complete bandwidth can be used in every CDMA cell, a much larger number of users can be supported in CDMA. How much larger? How many more users? Remember, we can only use bandwidth over 7, that is a fraction of 1/7 of the bandwidth. I can now use the complete bandwidth in every cell, which means I have 7 times the bandwidth I had previously. So, I can support 7 times the number of users that I could support earlier. That is the power of CDMA systems and CDMA networks, and this has property which is a very important property of CDMA cellular networks. As a name, this is known as universal frequency reuse, which is in every cell you are using all the available bandwidth, that is, you are universally using all the frequencies. Hence, this is known as universal frequency reuse, and this is a very, very important property of CDMA system. So, let me write that down. This is very, very important property of CDMA. So, CDMA systems, because they can use all the frequency in every cell, they are highly efficient in the usage of spectrum, which means you can support many more users in a CDMA network compared to a 2G system which is using TDMA and a 1G system which is using FDMA. I have not dwelt elaborately on TDMA systems and first generation systems, because as I said, the prerequisite for this course is a basic course on mobile wireless communications. So, you might have been exposed at some depth to both GSM systems, TDMA systems and FDMA systems in your first course. So, I do not want to dwell on those concepts again. So, the biggest advantage of a CDMA system, which is a third generation wireless communication technology, is universal frequency reuse, through which a CDMA network can support a much larger number of users for the same, given the same bandwidth. All right. So, that is the third use, and there is another very important use of a CDMA system, for which I have to slightly develop a bit more elaborate model. This is known as, first let me give the name. So, the fourth advantage of CDMA system, fourth advantage is what is known as multipath diversity. This is known as, it can extract multipath diversity. What is diversity? Remember, we talked about diversity at length when we talked about wireless communications in our very first lecture. We said wireless communication is a fading environment, it is affected by deep fade. So, diversity is nothing but increasing the number of links in your system, so that the diversity helps, that is, now you have multiple independently fading channels. So, you have diversity in your system, so that the probability that the system is in a deep fade is reduced, because even if one or two links are in deep fade, then the rest of the links can be used to convey the signal, right. So, diversity, adding more links in your wireless communication system, significantly helps the system by decreasing the bit error rate, by improving the reliability of the system. But we said there are multiple components in a wireless communication system, that is, signal can arrive from the transmitter at the receiver via multiple paths. We said these paths can add constructively, or these paths can add destructively. However, we have not said if there is any mechanism, so far we have not spoken if there is any mechanism which can separate these paths and add these paths up constructively. For instance, these paths we said add up destructively to result in a deep fade. Now, if I can somehow separate these paths from each other and sum them up constructively, then I am at a gain, because I have more signal power arriving at the receiver. I can add up to enhance the signal to noise power ratio at the receiver. So, if I can somehow add these different multi-paths components together constructively, that can result in a tremendous gain in the signal to noise power ratio at the receiver. However, that was not possible earlier because of the structure of the earlier systems. We are going to show now that in a CDMA system, because of a very novel architecture known as the RAKE receiver. So, the name of this architecture is the RAKE. Because of the RAKE receiver, I can extract these multiple components, not only extract them, I can add them up constructively, so as to always enhance the signal to noise power ratio at the receiver. So, now I can extract diversity not from multiple links, but simply adding these multipath components. This has a name, this is known as multipath diversity. This is known as multipath diversity in the context of CDMA systems, and this is another very important property of CDMA systems. So, let us begin our discussion on multipath diversity, or in essence, what is the RAKE receiver in a CDMA system and how does a RAKE receiver work. So, our next discussion for this lecture and the next is going to be on the RAKE receiver. How does the RAKE receiver work? How does the RAKE receiver help extract multipath diversity? For this, first we have to start, or I have to start with a basic description or a frequency selective multipath channel. So, let me first start by modeling a multipath channel. Remember, we modeled a multipath channel as multiple signal components arriving at the receiver. So, let me start with a model of a multipath Let me start with the model of a multipath channel. Multipath channel, the received signal Ym can be represented as H0 x of m plus H1 x m minus 1 plus H2 x m minus 2 plus H L minus 1 x m minus L plus 1. First, why is this a multi-part channel? Because look at this, there are multiple terms which correspond to multiple signal components arriving at the receiver. Now, forget this part that I have over here. If this part did not exist, that is Ym equals only H0 xm, then this is nothing but a flat fading channel. Remember, we talked about this, that incoming signal that signal at time m depends only on the input at time m. However, now look at this system, my output Ym at time m depends on xm, but it also depends on xm minus 1, it is plus H1 into xm minus 1 plus H2 into xm minus 2, so on, plus HL minus 1 into xm minus L minus. So, it depends on not only the current input xm, but it depends on L minus 1 pass symbol. Since, let me summarize this, current output Ym depends not only on xm, but also on xm minus 1, xm minus 2, so on xm minus L plus 1, that is, it depends on L minus 1 passed symbols. So, the current output depends on the current symbol and L minus 1 passed symbols. So, L minus 1 passed symbols are interfering with my current symbol. This is known as inter-symbol interference. Remember, we talked about this. This is known as inter-symbol interference. Now, remember, we said inter-symbol interference occurs when the bandwidth of the signal is much larger than the coherence bandwidth, and CDMA systems we said are wideband systems, because CDMA, because they employ multiple chips in one symbol time. Remember, this also we said in the past lecture, that CDMA system is a wideband system, since the CDMA bandwidth is much greater than the bandwidth of a conventional signal. Hence, naturally its bandwidth is going to be greater than the coherence bandwidth. Hence, naturally in the time domain that results in inter-symbol interference. That is nothing but what is represented using this equation here. This is Ym equals H0 xm plus H1 xm minus 1 plus H2 xm minus 2, so on up to HL minus 1 xm minus L plus 1. This is also known as a dispersive channel. Remember, in the frequency domain, since the signal bandwidth is greater than the coherence bandwidth, this is also known as a frequency selective channel. Hence, another name for this is dispersive channel, or we also saw that another name for this is a frequency selective channel. In time domain, this means inter-symbol interference. Look at this, this is similar to a digital filter. This is as if you are transmitting signal samples xm, xm minus 1, so on through a digital filter with response H0, H1, H2, and you are convolving the signal samples with the digital filter. Hence, this is similar to your channel is acting as a filter. You can think of your channel acting as a digital filter with filter coefficients H0, H1 up to HL minus 1. That is nothing but a frequency selective channel. All right, and this is also inter-symbol interference. Let me So, again illustrate here, xm is the current symbol, xm minus 1, m minus 2, m minus l plus 1 are the past symbols. So, let me just write it down in this. This is the current symbol, this is the current symbol, and these, the one in the big red block over here, these are the L minus 1 past. L minus 1 past symbols. Okay, and this causes intersymbol interference, which is also known as ISI. Okay. So, this is also known as ISI. So, now we have a multipath, a multi-component, multipath channel, which is resulting in intersymbol interference, because CDMA is a wideband system. Now, how can the RAKE receiver help here? That is what we are going to look at next. So, let us start with this frequency selective channel. Let us consider transmission of a CDMA system on this multipath channel. So, consider a CDMA system. Now, let us start with how can CDMA use this advantageously. So, let us consider a CDMA signal, remember, is given by multiplying the symbol of the user with the code of that user. So, I will consider a user 0. So, let me, xm is the CDMA signal, which is S0, that is the symbol of user 0, times the code of user 0. So, let me again illustrate the two components here. This is symbol of user 0, this is the code of, this is the symbol of user 0, this is the code of user 0. Hence, now I will pass this through this multipath channel. Let us see what we receive at the output when this CDMA signal passes through this multipath channel of channel taps, this H0, H1 up to HL minus 1, which are also the channel, which are the coefficients of the channel filter, are also known as the channel taps. I will write the output is nothing but, we said the output of the system is Ym equals m equals 0 to L minus 1, that is L minus 1 pass symbols are interfering. This is h of d, the coefficient h of d, times x of m minus d. Remember, this is a convolution, this is nothing but, let me write this down, this is nothing but a convolution operation plus n of m, where this is the noise. So, this is the noise. Now, let me look at the signal. The signal xm is nothing but S0 into C0 of m. So, I will substitute, instead of xm, I will substitute S0 into C0 of m. Hence, this is, I will write this as sigma m equals 0 to L minus 1 h of d. Xm is S0 into C0 of m, hence x of m minus d is S0 into C0 of m minus d plus n of m, that is the noise at the receiver. So, now look at this, because of the channel the code is being delayed, right, because xm minus d is affecting the code C0 of the user. Alright, this is nothing but my y of m. So, y of m, after passing through this frequency selective channel, this is multipath, this multi component channel, the output is m equals 0 summation to L minus 1 h of d S0 C naught, the code m minus d plus n of m. Now, at the receiver, let me illustrate, first start with an operation. I will tell you it might not be initially clear why we are doing what we are doing, but let us nevertheless start with this operation, and then it will be clear in due course of time why we have to operate or why the processing is done in this particular fashion. So, what I will do is I will first correlate with C0 of m, similar to what we have been doing. You have to remember, at the receiver of a CDMA system, you have to take the received signal of the user and correlate with the code corresponding to the user. So, now I am going to do that for this user 0. I am going to correlate with C0 of m. So, the first, let me call that as R of 0. This is the received statistic with correlating the signal of user 0 with code of user 0 with 0 lag. Hence, I will represent this as 1 over n summation m equals 0 to n minus 1 y of m into c of m. This is nothing but, remember we derived an expression for y of m, which is h d s0 c m minus d plus n of m. So, this is nothing but 1 over m equals 0 to n minus 1 s0 h of d times C0 of m minus d into C0 of m summation. Now, there is an additional summation over the path d, that is d0 d equals 0 to L minus 1 plus 1 over n summation m equals 0 to n minus 1 n of m, that is noise correlated with the code corresponding to user 0. So, I have divided this again into signal part and noise part. Signal component is S0 HD C0 m minus d times C0 m plus noise part is NM C0 m summation m equals 0 to n minus 1 divided by n. Now, the noise component we have seen several times before. This is noise Nm correlated with C0 m. This is summation Nm C0 m equals 0 to n minus 1 divided by n. We have seen this is noise of variance. So, let me denote this by n tilde of 0. This is noise of variance sigma n square over n. We have seen this many times before. So, let me now analyze this signal component, because that is slightly more, that is not that involves some analysis, because that is not straightforward. So, let me look at this signal component. The signal component is nothing but, let me write that down again, 1 over n summation d equals 0 to L minus 1 m equals 0 to n minus 1 S 0 h of d C 0 m minus d C 0 of m. Now, remember this has a summation for the L paths, that is 0 and L minus 1 interfering symbols, and summation over the chips m equals 0 to n minus 1. Now, I can split this into two summations. One is corresponding to the path 0, that is h of 0, and one corresponding to the rest of the paths. So, let me write this down as 1 over n. The path corresponding to 0 is nothing but S 0 h of 0 C 0 m minus d, d is 0 corresponding to the path 0. Hence, this is simply C 0 m into C 0 m summation m running from 0 to n minus 1 plus something for the rest of the paths. So, this is plus 1 over n summation d equals 1 to L minus 1. Remember, I have removed the 0th path. So, this is only from d equals 0 to L minus 1. Remember, d is really the path index, summation over m equals 0 to n minus 1 S 0 h of d C 0 m minus d C0 into m. Now, look at this, this is nothing but the first term. Look at the first term. In the first term I have C0 m, C0 m's, that is C0 m square, each chip is plus or minus 1, hence C0 square is 1, hence this is simply summation S0 h of 0 over m equals 0 to n minus 1, this is which is summation of 1 over m equals 0 to n minus 1, which is n. So, n over n, that is 1, hence this term here is nothing but S0 into h of 0. Now, look at this term in the inside, this is nothing but S0 HD times, look at this, this is C0 m minus d C0 m summation over m equals 0 to n minus 1. So, this is nothing but the correlation, the self correlation R 0 0, but with lag of d. Hence, when I correlate with C0 m at the receiver, the path 0 survives, that gives me S of 0, that is symbol transmitted by user 0 times the coefficient h of 0. However, for the rest of the paths, because the CDMA chip sequence has been shifted, the correlation with C0 m is nothing but R 0 0 d, which corresponds to the shift, and we know that expected R 0 0 of d is 0, because when you are shifting a CDMA sequence and correlating it, even though it is the same sequence, when you shift it, it behaves like a totally random sequence, hence the correlation, the expected value of the correlation is 0, which means now you are able to extract the 0th path, that is the path corresponding to h of 0, while suppressing all the other paths by correlating with C0 of m. Hence, this signal after correlation with C0 of m, which is R of 0, remember we denoted this by R of 0, this R of 0 can be written as S0 into H 0 plus n tilde of 0, such that sigma of n tilde square, that is the variance of this, is nothing but sigma n square divided by n. Okay. What else can we do? All right, I have correlated with C0 m, that is the chip sequence delayed by 0, and extracted the path corresponding to 0. Now, I can also correlate this with chip sequence delayed by 1. So, instead of correlating, so I can now formulate R1 simply as, or R1 simply as, I take the signal Ym correlate it with C0 m minus 1, that is instead of correlating with C0 of m, that is the code sequence m, what I will do is I will shift the code sequence by one chip and I will correlate Ym with this shifted sequence. That can be written as, let me write that down, that can be written as 1 over n sigma summation d equals 0 to L minus 1 summation m equals 0 to n minus 1 S0 h of d C0 m minus d into correlating with C0 m minus 1 plus 1 over n summation m equals 0 to n minus 1 n of m C0 m minus 1. Now, look at this, this is again taking some noise, correlating with, if C0 m is a random code, C0 of m minus 1, which is shifted code, is also a random code, hence this is nothing but again noise of variance. Let me call this n tilde 1, this is noise of variance sigma n tilde square equals sigma n square over n. However, now look at this term, look at this term over here. instead of correlating with C0m, I am correlating with C0m minus 1. Hence, this will pick the term corresponding to C0m minus 1. So, this will pick the term corresponding to D equals 1, because remember this C0m minus D into C0m minus 1 when summed over all the chips will only survive is D equals 1. Otherwise, for any other value of D, this will look like random correlation between two sequences. This will look like some R00 of D minus 1, which is 0. It is only survives if D equals 1, in which case it becomes C0m minus 1 square, which is 1. Hence, the summation is n divided by n is 1. Hence, this will pick the path corresponding to H1. Hence, now I can write R1 equals S of 0, that is the symbol, times H of 1 plus n tilde of 1. Proceeding similarly, I can correlate with C0 of m minus 2, I can correlate with C0 of m minus 3, so on. I can correlate, in fact, up to all the L paths, I can correlate with C0 m minus L minus 1, which is C0 m minus L plus 1. Alright. Hence, by correlating with the delayed chip sequence, I am extracting each path. Remember, previously all these paths added up randomly, but now I can separate each of these paths by the remarkable property of CDMA, which is I have to simply correlate with the shifted CDMA spread sequence. Hence, I can extract R2, which is S0 H of 2 plus n tilde of 2, so on and so forth. I have R of L minus 1, which is H S0 H of L minus 1 plus n tilde of L minus 1. And of course, we previously had R of 0 equals S0 H of 0 plus n tilde of 0. Hence, I can now in fact separate out these L minus 1 components corresponding to the L minus 1 multipath components that are arriving at the receiver, which I could not previously do in a conventional wireless system. Hence, now my net system model, as you can clearly see, my net system model, let me write it down, R of let me just say R of D, that is the dth path, is nothing but S0 into H of D plus n tilde of D. Remember, we have seen a model similar to this before. This is similar. Remember, we have seen a model similar to this before. This is like R of 0 is symbol into H of 0 plus noise. R of 1 is symbol 0 into H of 1 plus noise. It is like the same symbol which is being received at different paths. Remember, we saw this before when we said we have the same symbol, but we are receiving at different antennas, each with fading coefficient H0, H1, H2, HL minus 1. Now, we are saying because CDMA can extract these different paths, it looks as if at after correlation with each chip sequence, I have the same symbol S0 with coefficient H0. After correlation with M1, C0 M minus 1 delayed by 1, I have S0 into H of 1, so on and so forth, S0 into H of L minus 1. So, it looks as if I have L paths in which I am receiving the same signal. Hence, this is nothing but this is an example of in fact received diversity. This is nothing but received diversity. And why is this received diversity? Because look at this, the same symbol I am receiving via multiple paths. So, I have diversity. Now, I can combine this. In fact, we know right away how to combine this. We have seen something like this before. I can simply, so let us say I combine this as follows. I combine this using, so I combine this to generate statistics R, combine these R0 R1 RL minus 1 as R equals W0 R0 plus W1 R1 or W0 conjugate W1 conjugate R0 R1 plus W L minus 1 conjugate R L minus 1. We have looked at such a combiner before. This is known as a linear combiner. In fact, the linear combiner that maximize the SNR is nothing but the maximal ratio combiner. So, the linear combiner for SNR for XNR maximization combiner that maximizes SNR is nothing but the maximal ratio combiner, which is given as W equals H given by norm of H, where the system model is now given as R0 equals H0 into S0 plus n tilde of 0, R1 equals H1 into S1 plus n tilde of 1, so on and so forth. R L minus 1 equals H of L minus 1, I am sorry, this is H0 into S of 0 plus n tilde into L minus 1. I can represent this as a vector, hence this is nothing but vector R bar equals, I can represent this as a vector, this is nothing but vector H bar times S0 plus I can represent this as a vector, this is nothing but vector n tilde bar, and this is nothing but our receive diversity system. Look at this, we have seen a similar system in the case when we had multiple receive antennas. Now, we have multiple paths which we are able to isolate because thanks to the RAKE receiver. All right. So, this is the receive diversity in a CDMA system, and the optimal combiner R is generated, the optimal combined statistics R is generated as W bar Hermitian R bar, where W bar which maximizes the SNR is given as W bar equals H bar divided by norm H. All right, for the optimal W bar which maximizes the SNR is given by S. Now, let us use this W bar to see what we get. We know R bar equals H bar times S0 plus n tilde bar, hence W bar which is nothing but H bar divided by norm H, hence R equals H bar divided by norm H Hermitian into R bar, which is nothing but H bar Hermitian divided by norm of H times H bar S0 plus n tilde bar. This is nothing but H bar Hermitian, H bar which is norm H square divided by norm H. So, this is norm H into S0 plus H bar Hermitian divided by norm H into n tilde bar, and we have seen this in the case of maximal ratio combining before. The SNR, the signal power, is nothing but the power in this, which is norm H square into power 0 over the power of noise, hence the SNR. So, this is the signal, this is the noise, signal power is norm H square times power of the signal, which is P of 0, plus noise, which is of power sigma n square divided by n. Hence, SNR is nothing but norm h square P divided by sigma n square over n. This is nothing but the RAKE receiver. So, this is the RAKE receiver for CDMA. So, this is nothing but where you are extracting those different multipath components by correlated with the shifted chip sequences and combining them using the maximal ratio combiner is nothing but the RAKE receiver in CDMA systems. Because we are short of time, I will end this lecture here, and in the next lecture I will again briefly touch upon this. Although it is now clear, because we have posed it as a multi antenna problem with received diversity, it is immediately clear why this has received diversity, but I will again, just to remind you, will touch upon this point in the next lecture and then we will proceed from there. Thank you very much.